Hi, this is Alessio Ferrari again. In the next minutes, we will try mainly using some examples to state the different approaches that may be used in the context of a landslide hazard assessment. Let's start by trying to clarify what we intend for landslide hazard assessment. Hazard analysis is a fundamental component of risk assessment. For a given situation, we always need to start with collecting data in order to identify potential instabilities. Each potential instability, the danger, needs to be analyzed with specific tools. The final aim of this operation is to identify the susceptibility of given areas to potential danger. Assessing the susceptibility is an operation which has a qualitative focus, while hazard analysis is performed to provide a quantitative assessment of the possibility of a landslide to occur and to identify possible hazard scenarios. Each potential danger must be characterized identifying with the maximum possible precision the phenomena which may occur, namely the type of landslide that could be initiated or activated, what is the extension of the phenomena, and the area that can be potentially affected by it. The intensity will provide an indication on the severity of the phenomena. All these mentioned elements, which are part of the landslide analysis, are fundamental ingredients in order to assess the consequences related to the phenomena. In particular, the study of the type of danger and the area that are affected by the landslide will serve to identify the elements which are at risk. At the same time, the intensity will serve as an ingredient, together with the vulnerability of the elements, to quantify the consequences. Even for the case of a simple rock block falling, the quantification of those ingredients may require dedicated analysis. In this particular case, we will need to know the mass and positioning of the block that is likely to fall, the area that can be affected by the fall that will depend mainly on the trajectory of the block, and so the elements that could be impacted can be identified. The speed of the block could serve as an indicator for the intensity, which would let us computing the potential damages done to the infrastructures or buildings impacted by the block. Also, the definition of occurrence probability is part of the hazard analysis. Together with the quantification of the consequences is the key ingredient to compute the risk. The example of the block that we've just discussed is already anticipating how complex hazard analysis for a landslide can be. Scientists and stakeholders often try to overcome this complexity by using simple approaches. Here we see the example of an hazard analysis for rainfall-induced landslides. By collecting information on past events, here in terms of rainfall intensity and duration, for which a landslide has been produced, it appears reasonable to draw thresholds like those reported in the figure, for which we can identify events that have produced landslides and events for which landslide was not produced. A threshold like this could be used to make hazard assessment. Interestingly, one could relate the occurrence probability of a landslide to the occurrence probability of a rainfall event that may produce that landslide. A tool like this seems very promising, and it is probably the very first type of analysis that one could do when it's called to operate in a given area, especially when no extended databases are available. However, severe limitations apply. A method like this can have just a regional validity because it can apply it just for the area for which the rainfall and landslide occurrence data have been collected. There is no physics in it, so we are not going really to see what are the physical processes which are triggering the landslide. And when you have no physics into the process, it's very difficult to make any kind of forecast. Does not require too much expertise. It's quite a simple method, doesn't involve the use of particular instruments or software, but needs to be updated as soon as new data on landslide occurrence event are registered. A different approach consists in performing hazard analysis, trying to include as much as we know in terms of the physical phenomena which are involved in the processes. This is the case of a simple deterministic approach that can be used to analyze translational slides. It applies to shallow soil covers or existing discontinuities parallel to the slope when the length of the landslide body is much higher than the thickness of it. Translational failure mechanisms with surface of rupture parallel to the slope can be analyzed thanks to the infinite slope model. Thanks to the elongated shape of the landslide body, we can make the hypothesis of an infinite slope. We can isolate a portion of the slope and write all the forces which are applied on it, starting from the weight, considering the forces which are coming from the interaction of the isolated mass from the surrounding masses, and the resulting forces which are coming from the pore water pressure distribution inside the landslide body. The ratio between the resisting force and the destabilizing force give us the factor of safety. Factor of safety is a very clever way to define and to assess the stability condition of a given slope. The higher this number, it means that we are far from a possible failure of the slope. In this slide, we see how the general formula that we just seen for the factor of safety can be easily adapted to different conditions by considering different scenarios for the pore water pressure. This is the case for a fully immersed slope underwater. If the water is moving inside the slope, in the particular case in which we have flow lines which are parallel to the slope, this is the final formula that we get for the factor of safety. The infinite slope model that we've just seen is a very effective way to compute the stability or to assess the stability of a given slope that can be used if we are in this configuration that we described at the beginning. Still, many assumptions are included in the analysis. It's a method that requires professional civil engineering knowledge. The selection of the parameters that are entering into the analysis should be done with a given experience in dealing with this material, so it's always better to be advised by geotechnical engineers which know exactly how to compute the shear strength parameters in terms of C' and Φ'. Software is not a must, but it can help, especially if you are going to repeat this analysis for different configurations. Forecasts are possible. We have seen that by changing the regime of the pore water pressure into the slope, how the water is moving or resting into the slope, we can anticipate how the failure condition can be produced or not, and the probabilistic approach can also be included if we make the parameters that are entering in the definition of the factor of safety that are evolving with a given probabilistic law. We will now see the example of an advanced modeling for hazard assessment. A more advanced model can be used enhancing the physical description of the involved phenomena, but of course, more information are needed as model inputs, and high-performing tool for computation should be used. This is the general outline that we can use when we are dealing with more advanced modeling. More advanced modeling offers a lot of advantages. Of course, there is a price to pay for it. We are dealing with more complex analysis that require a lot of knowledge about complex physics that you want to involve in your analysis. Most of the assumptions are addressed, but in order to do that, you need very high quality data. High-end software is a must. Usually we need quite articulated or advanced numerical codes, like using finite elements in order to solve all the complexity which we are putting in our problem. Let's now summarize the main points that we have discussed in this video. Empirical models are based on past events, and they could serve as a simplistic model or approach to deal with landslide assessment. Physically based models, although simple, they provide the possibility to include in the analysis the knowledge about the slope geometry and the characteristics of the involved materials. Advanced models are very powerful tools to perform landslide hazard assessment. Relevant features can be incorporated. We can add as much as complexity we want, trying to include as much of the physical phenomena that we think are relevant for the process that we are analyzing. Physically based models, simple as the infinite slope analysis or complex, they offer the possibility to assess and design also mitigation strategies.